All right, so we are going to look at population growth models. You have seen this image before, so what we see here, two different growth models, and we're going to talk about kind of where these come from and how we interpret these graphs a little bit more. So first thing I want to do is I want us to just do a quick review of being able to read graphs in general. So it may have been a while since the last time that you were trying to read a graph, and so we're going to do a little practice with that before we jump into the more specifics that have to do with the population growth models. So here I can see that I have a nice line graph, and up at the top I see the title of my graph. When my resources are nice, they give me a title, but they don't always. A nice organized graph will always have a title and then our axis labels. So our title is the number of tadpoles in a pond. And what we're looking at is how the number of tadpoles changed based on the year. And this is going to be kind of similar to what we're looking at with population growth models, because we are looking at population sizes. So this will be a nice kind of direct correlation with that, even though this is a totally different kind of model. It's not a growth model. Clearly something weird happened here. This isn't just a normal population growth. So just looking at this, in 1990, all I do to find how many tadpoles I have that year is I find the height of my graph in that year. So I'm going to go over to 1990, and then I'm going to go up to however high it is. And then I have to figure out the scale. So this one goes up to 2,000, and every 2 blocks is 400 tadpoles. So that means every 1 block must be half of that, must be 200 tadpoles. So that means in 1990, I had 200 tadpoles. If someone was to ask you, for example, what year were there the most tadpoles in this pond, then what you would want to do is figure out, okay, well, at what point in my graph is the graph the highest? Where do I have the most tadpoles? So I want to say, looking at my graph, where is the highest? That's going to be right here. So that means the most tadpoles I ever got was between, we said each of these is 200, so it's between 1,400 and 1,600. So the most tadpoles I ever got was about 1,500 tadpoles, and that happened in the year 1992. When we're looking at graphs, we can also talk about how the overall patterns are changing. So if I look from the year 1990 to the year 1992, I have a linear pattern. This is forming a straight line. I have a linear growth pattern here. So I can see that the number of tadpoles is increasing in a linear way. From 1992 to 1993, it's decreasing, because from 1992, I went from 1,500 to 1993, I had about, let's see, that would be about 300. So I have a decreasing rate here. And then we can also talk about where it's growing faster versus slower. So if I look from 93 to 95, it's growing again, but it's not growing as fast as it was here, because if I look between just any 2 years, this is moving from about 300 and let's say 70 tadpoles-ish to 400 tadpoles. So it only increased by 30 tadpoles this year. Compare that with an area that has a faster rate of growth. Looking at just 1 year, between the year 1991 and 1992, I increased by 1,500 minus 800. So I increased by 700 tadpoles there. So we can see, because it's more steep, that means that it's growing faster. And because it's not as steep here, it's still increasing, but not as fast. And we'll use all of that while we're talking about our population models. So looking back at this diagram, so these are our population models, and now hopefully it's a little bit easier to read what's going on. So what we have in the blue curve is what we call exponential growth. And we said exponential growth is where our population just keeps growing and growing. So if I look at the population represented by A, the number of individuals is just growing and growing and growing. I'm not sure if my mouse is still showing up. Hopefully it is. I can't see it. Oh, there we go. Okay. So it's just growing and growing. So this happens, this kind of exponential growth happens when whatever organism that is has unlimited resources. There's nothing stopping its growth. It's just going to keep on going. And then B, we said this has a section where it's growing and growing in here, and then it starts to slow down a little bit, and eventually it kind of levels off. And we said that point where it levels off, we call that the carrying capacity. And this is more what happens in real populations, we said. We can also call curve A the exponential curve. We can say it looks a little bit like the letter J. We can kind of see a J there. So we sometimes hear that called a J curve. And the logistic curve is sometimes called an S curve because it has this piece and then slows down and then has this piece. So it almost looks like an S. And so those are some terms you may hear. So now let's look at more specifically what's actually happening within these populations that would lead to these kinds of growth. So the first thing I want to do is I want to model an exponential growth. So in this situation, let's pretend we can go back to the idea of tadpoles, sure, because they're the animal we have on our brains, right? So let's say we have tadpoles in a pond. They're just coming to this pond. There are unlimited resources because there's very few tadpoles. Let's say 2 tadpoles are moving into this pond. And those 2 tadpoles have all of the pond to themselves. They've got unlimited resources, so they immediately can both reproduce, and then they are going to double their population really quickly because they've got so many resources. And at this point, they still have, so we've got unlimited resources, right? This is in our fake scenario where we have unlimited resources. That means my population just can double every single year. And if my population just keeps doubling and the resources are never limited, then what happens is I get this sort of J pattern. And so all I did was I doubled my numbers every year there. And then you don't have to know how to get to this formula, but I just wanted to include it so that you could see how that curve will change over time. So it's just going to keep on growing and growing. If I was to even zoom out and look at 30 years from now, that number is so big that I can't even get to it on my graph without zooming way out. So by year 8, we have over 700 from a starting number of 2. So we grow really fast when we talk about exponential growth. And again, this isn't really what happens in real populations, because in real populations, we have a limit on our resources, right? We don't have an infinite number of resources. Those tadpoles all have to eat. And if they all live in the same population, that means they all live in the same area. So they have to compete for those resources. So in reality, what happens? So this red is our exponential model. That's not what happens in reality. In reality, what happens is we have what we call a logistic model. So at the start, we still have those 2 tadpoles come in. And since there's only 2 tadpoles, they are going to start to double pretty quickly because at first, they do have what feels like unlimited resources because they can just use, there's more resources than they can even go through. So at first, we are going to get this exponential growth. So we can see that at first we are fitting this red curve. We're fitting that exponential growth curve. But then what starts to happen is we say, well, maybe we're starting to run a little bit lower on our resources. We're starting to compete. So maybe not every organism gets to double. So instead of doubling from 16 to 32, let's slow it down a little and say, well, maybe we don't quite get to 32. Maybe we get to 27. So, okay, well, now we've got 27. That's even more. To try and double those, we would need even more resources. So we're going to need to slow down even more. So instead of doubling from 27, we're going to go, instead of, maybe we get to 40. We don't get quite up into the 50s like we would if we were to double it. And then if I was to double 40, well, then I'd get all the way to 80. And I think we're running kind of lower on resources now. So I don't think I can get all the way to 80. They can't all double because they're competing for those resources. And so we start to slow down even more and then even more. So notice it's still growing, but it's not growing by as much. So instead of going up 100% each time, it's going up a smaller amount. It's not going up by a smaller number, but it's going up by a smaller chunk of the overall. So it's growing more slowly because it's starting to have limited resources. Let's see. I think I skipped a number. And the reason I'm doing this is just because I do want it to fit into my curve. So we've started to grow more slowly. Now we're going really, really slowly. We're only able to have, now our birth rate and our death rate are probably getting to be about equal. Our population is using up about all of the resources that it has without killing the population. And so we're really growing pretty slowly. And then eventually we're going to reach this point where we can't really grow anymore. Because I can only have enough resources for so many organisms. And if I was to keep growing, I wouldn't have enough to sustain that system. And so that's where that leveling off comes in. And that amount that we reach, where we're like, well, there's not really enough resources to keep on growing, we call that the carrying capacity. And so if I was to fit a curve to this and see what the pattern would look like in the future, we're never going to get past this amount of 80. That's going to be the most that we can do. And so we call that our carrying capacity. The last thing I want to address is, in reality, sometimes we don't have it grow so nicely because it's not like our population sitting there and saying, well, we've reached our carrying capacity, therefore we need to stop using our resources. So in reality, sometimes we see it modeled a bit more like this, where we reach our carrying capacity, and then the organisms are still going to keep using their resources because they're still there, but then there isn't enough for all of the organisms. They've used more than they should have. They've used more than their take. And so what happens is there's not enough for everyone to survive. And so that death rate increases, which causes a dip in the population back below the carrying capacity. But then, because they've dipped below, now they have enough to sustain that amount again, but they're stingy, so they use too many, and it's so on and so forth. So they use a little more than they can sustain, which causes some of them to die. So they use a little more than they can sustain, and then that causes some of them to die, and so on. And so this can be kind of what the more realistic model looks like. And if you see it framed like this, just know that that carrying capacity of what they actually can sustain is somewhere in between where they overshoot and then where they dip. So it's this line that fits in between that curve. So this and this blue curve are both showing the same type of growth. These are both logistic growth. This is just kind of an idealized logistic growth where we would say, okay, we reach nearly the carrying capacity, and then we stop because the population can't keep growing beyond that. Or in reality, maybe they go a little bit past it, and then they cause some of their organisms to die, and so on and so forth. But these are both logistic models of growth, which is more realistic than, of course, the exponential model. So what you'll notice is in my logistical model, I have an exponential growth phase. So there's a point where my curve matches nearly exactly to that exponential curve. So there's a point in my population growth where I am having exponential growth, but then my growth slows down. And that's because of my resources. And then eventually it slows down even more. Look how closely together those points are. It slows down even more to try and reach that